Hi everyone, my name is Andrew Mogowan. I'm a senior engineer here at KX, and I'd like to tell you about detecting anomalies and patterns with temporal similarity search. So the first thing I want to do is talk about what that is and where it came from. So temporal similarity search stemmed from our journey into the world of unstructured data, where the concept of similarity searching is used within the vector database space. So what we did is we took that concept of similarity searching and we have applied it back to the structured time series data world. Temporal similarity search is a proprietary search algorithm where the search will scan through your data set and create a result for each record and its following vectors. No index or vector embeddings are needed, and so this is well suited to your existing temporal data that may live in a KDB Plus database, or data can easily be inserted into this database. So let's take a look at the architecture of what we're talking about. So it comes in the form of a Docker container, which primarily has worker nodes that execute the searching itself. On the left-hand side, you can see that you can interact with this Docker container via three methods, via REST, Q, or Python clients. So allowing this to easily integrate into various types of workflows. Over on the right-hand side, you can see that you can use your existing KDB Plus database by mounting that to the Docker container. This will allow you to access your existing database, and there's no need for data duplication. The other option is that you can insert data directly into the database within the container itself if you don't already have your data on a KDB Plus on this KHDB. So for this demo, the background is that I have a week's worth of market data for the Tesla stock. I have the price and volume bucketed by second. And what I'm going to do is I'm going to insert the first 4 days of this week of data into my database. And then I'm going to replay the 5th day to mimic a live data feed. So before showing the demo, let's query that data to show how it actually looks. So you can see here by running the query that I have, as I said, 1 record per second for the first 4 days for the Tesla stock. I have the sum of the volume and the average price. And the key thing to note here is that we have no vector embeddings. So we haven't had to prepare the data specifically for this functionality. So we have 2 sets of use cases that we're going to look at. The first being anomaly detection in live data. So in this case, what I'm going to do is take my live data as my search pattern, and I'm going to search for that pattern against the data that is already in my database. I'm going to return the nearest neighbors or closest matches to my search pattern, and then I'm going to highlight the result when it is a certain distance away from my live pattern, because that will determine or show me anomalies. So this might be easier explained via the graphs within the demo. So let's get running here. So don't worry too much about the code that I'm running. It's just a function with a few arguments. What we're more interested in are the graphs that are going to be produced. So in this case, there are going to be 2 graphs that are outputted to me. The top graph is our live pricing data, which updates every couple of seconds. So every few seconds, I'm getting some new data points, and then I'm continually displaying the past 3 minutes of data, or 180 data points. As I receive those new pricing updates, I'm taking my live pattern as my search pattern and executing a similarity search for that pattern against my data historically and displaying the results in the bottom graph below. So you can see that my live pattern here is on August 7th, and my closest matches are on August 3rd in this case. Now, this is all great. I'm able to display my nearest neighbors or closest matches. But what I'm more interested in is when that pattern actually differs to its nearest neighbors. And that's when this line above will turn red. So you can see that we've just managed to identify an anomaly here in that our live price pattern is a certain distance away from its nearest neighbors. And so we're identifying it as anomalous behavior and highlighting it in red. So if I just pause this and we can go down and take a look at the explanation of what's actually happened here. So Elon Musk actually sent a tweet on August 7th at 12:48 to say that he was going to take Tesla private. If we come back up to our live pricing chart, you can see that at 12:48 and 15 seconds, the Tesla stock price started to dramatically increase. And it was at that exact point that we were able to identify this price pattern as anomalous behavior, because we had not seen a pattern similar to that in the data that we were searching against. So one thing to note here is that I've been using a search pattern of length 180 data points for the past 3 minutes. But if we come back up to the data that we're searching against, and we noted previously that there are no vector embeddings, the benefit of that is that we are not tied to a fixed length of a search pattern. So we can use a search pattern of any length. And in my next example, I'm going to change my search pattern to be just 60 data points or 1 minute. So if I run this, we're going to get the same sort of output as before. This is later the same day, and I'm displaying the past 60 seconds or 60 data points of data. Just like before, every few seconds, I'm getting some new updates, and I'm continuing to execute a similarity search of this search pattern against my data historically and display those nearest neighbors in the graph below. And just like before, I'm getting another anomaly after I let that run for a period of time. And it's quite clear to see here that this anomaly has been caused by the fact that I have stopped receiving any price updates. And so this has created a pattern that has not been seen before in the data we are searching against. So to explain what's happened in this case, is that NASDAQ actually halted the trading of the Tesla stock at exactly this point in time. And so we stopped receiving any price updates, which created that anomalous behavior. So far, we've only been looking at the metric of price. There's nothing to stop us from looking at any other metric. So what I'm going to do is also look at volume. But instead of just looking at volume instead of price, we're going to combine the two. So what I'm going to do is I'm going to continually execute searches of my volume and price patterns. And I've decided that I only want to be alerted of anomalous behavior when both my price and volume metrics are exhibiting that anomalous behavior. So let's run this and view the output. So we're just getting one graph, but we're displaying the two metrics on this graph. So we have our line, which is our price, and we have our bars, which is our volume. And you can see that they will both continually update, and we will only highlight this graph in red when both are exhibiting that anomalous behavior, like we are just seeing now. So this is allowing me to analyze multiple dimensions simultaneously rather than just the one metric. So this functionality, so far we've been looking at detecting anomalies in our data. And let's just take a look at the use cases that we can apply this to. So from one of the examples that we saw previously, when we stopped receiving price updates, you can see how we could use this temporal similarity search to proactively address our data feed issues or continually monitor our feeds. Other use cases that we could apply this to would be to be looking at unexpected deviations to address those order performance issues, or within sort of more surveillance style use cases, looking at market abuse, toxic order flow, and so on. So our second set of use cases focuses on pattern matching rather than anomaly detection. So what we're going to do in this case is use the same functionality of temporal similarity search, but we're actually going to reverse the way in which we're using it. So we're going to define a pattern in advance. And as we receive live price updates, we're going to insert that directly into our database and search against that live data for the pattern that we have defined in advance. So let me run this and we can take a look at the output that's displayed. So I'm just going to pause this for a second. So you can see here that we have a couple of graphs. Just like before, our top graph is our live pricing chart. So every few seconds, we're actually going to get a full new minute of data. So we're going to play this on sort of fast forward. On the bottom left here is a pattern that we have defined in advance. This is our red line. So I have decided that I want to continuously be looking for this M-shape pattern that I defined in advance, and we're just displaying it here so we know what we're looking for. Then over on the right-hand side is a historic search of that M-shape pattern. The reason that we're doing that is actually to take a look at the orange points. These orange lines are the prices that occurred after the M shape over the past week of data. So when we found the M shape over that past week, here we're able to see what happened next. This can then allow us to start to create predictions and forecasts of what we think might happen following the next time we see this M shape in our live data. So let me run this and hopefully try and catch one of these patterns. So we're only going to display the pattern if we actually find it below here. So far we haven't managed to find one, but hopefully we will soon. And let me just pause that, because here we've displayed this M-shaped pattern. We've managed to find that in our live data and we're printing it below. So if I come back up to the live pricing chart, we can actually find that M-shape over here on the right-hand side. So we've successfully managed to find that M-shaped pattern that we've been on the lookout for. Now, in a real-world scenario, you're going to likely be continually searching for a lot more than one pattern at a time. With our search API, you can actually pass multiple patterns into the search argument to allow you to continually search for multiple at the same time. But for my demo, I've only looked at one. So now let's take a look at the use cases for pattern matching. So pattern matching can be used for allowing us to capitalize on trading opportunities or to optimize our trading strategies. Or also we can be mitigating risk by detecting patterns of interest that might require corrective action. So that brings us to the end of the presentation. Just to sort of recap on what we've looked at. Temporal similarity search is a proprietary search algorithm. This is available now. If you would like to try it, please reach out and we can get you set up. Thank you very much.